All right. Hi, everyone. Um, Good morning. I'm a geophysicist. I have a lot of astro data in my plots. I'm sorry when I make mistakes. We're just plotting. So, okay. Yeah, so I'm just going to be working through some notebooks that are up in the workshop repository. I did push some changes past couple hours, but I don't think it'll matter. It was mostly kind of like the narrative overview stuff. So don't worry about pulling those in unless you really care. But so we're in this day one lesson 6 plot folder. And let me get rid of that. So the plan is to walk you through some of the basic stuff about YT plots, do a little bit of live plotting, and then depending what people feel like, we're going to have sort of a choose your own adventure style plotting session where you can either choose to go off and everyone work on all the different notebooks I've semi-prepared, or we could have a vote, pick one or two, and I could walk through them with you. So that's kind of what I'm thinking for this, because the goal is to not just show you the plotting, but make some plots that utilize all of the stuff that we've talked about already. That's what we're going to try and do. Right, so plotting in YT. The YT has a number of plot types in the plotting API. And as Matt was talking about this morning, these are all ways of reducing your data in such a way that you can show something on screen. So there are kind of some general categories. So there's spatial plots, which are reductions in spatial dimensionality. So it lets you take your 3D volume and represent it as a 2D image or 1D image. So we have slice plots that are, you take a plane, cut it through your data, and wherever your plane intersects your data, create an image that represents the field you want to see. So that's your slice plot. Projection plot, very similar. You have a plane slicing through your 3D volume. Instead of just sampling your field, it projects rays through the volume and accumulates data along rays and deposits it on your image plane within the plane that you've defined. And so those all take your 3D data, reduce it down to 2D. And then we also have our 1D line plot on the right here, which is just casting a ray through your volume, sampling at a specified number of points and giving you some output as a function of length along that ray. So for all of these, for these 2D plots, they can be either aligned with your axes or off axes. So this just determines the orientation of the plane. So if it's aligned with an axis, it's just normal to one of your 3 axes. If it's an off-axis plot, it's oriented arbitrarily by some normal vector that you supply. And generally, I'd say with YT 4.4, we have pretty good interoperations between all the gridded and the particle, at least the SPH particle data, so that the slice plots and off-axis and projection plots both work on an off-axis for SPH data. And then there's also the separate kind of particle plotting API, which just kind of splats little pixels for all your individual particles and accumulates them onto an image plane for you. And so those are all kind of the spatial, what I think of as the spatial plots. And then there are also the statistical plots. So these are 1D and 2D bid statistics with optional weighting parameters. So there's the profile plot on the left, which is just one field against another field. And then the phase plot on the right is a 2D version of that, where you have the different fields on the axes and then they're coloring by a third variable. And we're going to walk through how to actually plot all these, but yeah. And finally, we have all the volume rendering API. So this is another way to take 3D spatial data, reduce it down to 2 dimensions, similar to the projection plots, except the accumulation along the ray is a little bit different. And we're going to get into that tomorrow. So that's all I'm going to say about those.
What is that on the left? That doesn't look like astro data.
That's not astro data. That's a seismic tomography model of the Western US upper mantle. White bit there is Yellowstone.
Looking.
Cool. Okay. So in general, how you use YT's plotting API. So first step is you generate a plot initially with some settings, optional arguments and keyword arguments. And then there's a whole bunch of optional callbacks that you can use to modify that plot. And then after you just add all those things on, you call something to display or save that plot. In terms of what the callbacks are, so at least the way I think about them, there are what I think of as more like plot adjustments. So like, let's say you have a plot and you want to modify some element of that plot that already exists. There are a whole bunch of methods that start with set underscore that will modify elements. Plot annotations are callbacks that add new data to an existing plot in some way, and these generally start with annotate underscore. We're going to walk through some simple cases here first. Okay, so I think this notebook, we're just using an isolated galaxy for everything. What we're going to stick with. So this is just an example of this sequence of the generating the plot object with the callbacks. So first thing, we load up a data set here, create a slice plot, yt.sliceplot. You provided the data set. In this case, this is going to be an axis aligned slice plot. So you provided the axis that you want to be normal to your slicing plane, the field that you're going to plot, and I'm also supplying the width of the resulting plot. Come back to that in a second. There are some modifications to that plot using these set CMAP and set axes unit. I'll also come back to these, and then some annotations. Let's actually just run that. And cool. So we get out this plot here. So just jumping back up here. So the width argument to the slice plot is controlling the actual width here. If you don't supply that, it'll just go through the whole domain. Annotate grid and annotate velocities are callbacks that go and add data related to a specific field. So the annotate velocity is adding all these little arrows here, and then the annotate grid showing the, in pretty faint, I don't know if you can see them up there very well, but the actual boundaries of the grid for this, or the grid boundaries for the galaxy data set. Yeah, so that's just kind of showing you the sequence of make the plot, modify the plot, plot the plot. Yeah, so here, I think I'll do, just to slow myself down a little bit, is we'll go through and actually walk through creating some of these plots, manually, just to make sure everyone is a little bit familiar with the plotting API before we do more interesting stuff. Okay, so generally when I make plots, I like to kind of sort the output in an object. So I'll say slice equals something. If you don't do that, you can just make a plot and it'll show you the plot, but it's nice to have a handle available to make modifications to. So make a slice plot, yt.sliceplot, give it the data set, give it the axis that you want to be normal for the slice, and give it the field. Let's run that. So you get the field out. Cool. So, and that's an axis aligned slice plot. To orient this arbitrarily, all you have to do here is, instead of providing a string here for the axis that you want to be normal, is you provide a normal vector for the image plane that you want. So if we set this to 1, 1, 1, this will be something that's cutting through the obliquely through the domain. It would be very large. So what you end up getting out is this funny little what's that X1, 1, 2, 3, 4, 5, 6 that comes from slicing directly diagonally across the whole data set. Because we are not oriented normal to a slice. Yeah. And then projection. Let's move on to projection plot. So for projection plot, very similar. Give it a data set, give it an axis, give it a field. See what comes out. So in this case, we're casting rays through our volume. accumulating density along the way. So the units you get out here are projected density, grams per centimeter squared. And if you were to multiply each pixel area by that, you would get the total mass in that little pixel. And so the projection plot has a lot of options here. So you can also, for projection plot, you can also give it a arbitrary normal vector as well. But let's see some of the things. Okay, so all right, the doc string for this doesn't carry over everything, does it? Okay, so the top level projection plot has some code in there that automatically decides whether you're doing an axis aligned projection plot or an off axis. But I think, yeah, okay. So if you look at the doc strings for either the underlying axis aligned or just off axis projection plot, you'll get all of the specific arguments. And so there's a lot here. So yeah, so there's a lot here. We're not going to go through a lot of it right now. Some things, let's see, some important things. So center determines the center of your plot. So all of these plots I've done so far are just oriented right in the middle of your domain. If instead you want to be oriented some and have the center of the plot be some other point in your domain, you set that center to that value. Do a lot with that. Other important things to that's kind of all I wanted to touch on for that so far. And yeah, so those are the the 2D images, and those work well with both the gridded data sets as well as SPH data sets. And the line plot above is generated with this line plot command here. So just yt.lineplot, you give it the data set field, start point, end point of your line going through the domain, number of points you want to sample, and you get out your plot here. Nice. Okay, cool. So let's move on to these profile plot, base plot. So very similar to everything else, except for the profile plot, this first argument actually expects a data object. So if you wanted to plot a profile or phase plot for your whole data set, you would just give it all data. You could supply here anything else you want. So you could do a region, give it some arguments, or a sphere. But let's keep this at all data.
You can also do it for projection plots and slice plots.
Yes. Which one in the notebook is about that. But for these slice plots, all these have a data source argument that you can set to any data source you want. Or can you replace the DS with the data source? I don't know.
You can't.
It's got to be.
I don't know.
Yeah. Yeah, and one of the notebooks that I have ready will let you explore that a little bit more. Cool. Profile plot. Yeah, so your X and Y axes, optional weighting field, and you get a profile plot. Phase plot, similar, you give it a region, X axis, Y axis, and then the field for the Z axis that you want to color by, and you get out your phase plot that shows your mass distribution as a function of temperature and density. So sometimes, especially since I'm coming from a background where like I work with a lot of just like kind of uniformly gridded data, and I often just like want to see a histogram rather than sort of a weighted bin statistic, which is what the phase plot really is. And so sometimes I just want a histogram. So the first question, if you find yourself in this situation, is to ask yourself, are you sure you want a histogram? So for example, for this data set, there is a slice plot through Enzo tiny cosmology density field where we are using this callback to annotate all of the cells, cell edges in this slice. So what you see is the underlying variable resolution structure through this domain. And one of the index fields that Matt did not touch on this exactly, but it popped up on screen if you were even outside, is for gridded data sets, there's this index ones field. So what this is a field that is equal to 1 inside every grid cell. And so if you make a projection through your data set of this index ones field and change the projection method, which I'll come back to for a second, run that, what you get out is a plot of the cells in your data set across the whole domain. So this projection method here controls how data is accumulated along your rays in your projection plot. So a sum is just a straight sum of every point encountered along the ray. The default is, I think, just integrate or integration or something, integrate. And in this case, you see uniform value, which is equal to, should be equal to just the length of the domain, I think, because it's just integrating the path across. But so this plot here of just the number of cells encountered along each of your rays is why you probably don't want a raw histogram if you're working with variable resolution data, because the raw counts of data in your data set will reflect mostly the underlying grid structure rather than something related to your field. So understanding that, maybe you still want a raw histogram. So if you either have uniformly gridded data where this is not the case, or maybe you're doing some sort of debugging, you can make a raw histogram with the phase plot by giving it your X and Y variables and then just counting up your index ones plots. And then what you get out is for these temperature and density ranges, the colors here are just the number of cells that have that value. So it's not necessarily a physical thing that you're interested in your analyses, but it is a useful debugging tool, I think. I often do, but yeah, cool. So before getting into some more interesting stuff, just a couple notes. So I don't think we've talked about non-Cartesian data very much yet, and I'm not going to talk about it now, but I will talk about it tomorrow a little bit. But not all of the plots work for all of the coordinate systems. Generally, for spatial plots, if you don't have a Cartesian data set, you'll get axis-aligned slicing only, and you will not get any volume rendering. Although tomorrow I'll talk a little bit about volume rendering for data in spherical coordinates. And then if you have data that's not grid-based, so SPH data, pretty good, but no, I don't know that the volume rendering API actually works at all, because yeah, so you don't get volume rendering, but you get good slices and projections now. If you have other data sets like unstructured grids, pretty much only get slicing. Although the phase plot and the statistical plots, I think, work for everything.
Well, you can always do a phase plots in the X and Y.
Yes, yes. Oh yeah, that's true.
Yeah.
I think the volume rendering also, it does first intersection. So you can get like surface.
Oh, for the meshes.
For the meshes.
Yeah. If you install Embry separately.
Yeah. I thought it didn't require Embry anymore. It does it.
We're not going to do that tomorrow. Yeah, and then a lot of the plot annotations by their name, you can kind of see that they will require certain fields. So like annotate magnetic field is not going to work if you don't have magnetic fields in your data set. And annotate mesh lines only works for unstructured grid. Okay, so that was your crash course intro to all the sorts of plots that are in YT. So for the next, I guess, 40 minutes or so, you get to kind of decide what you want to do right now. So in this directory here, there's these other 5 notebooks that are all kind of just like notebook exercises. Like if you open them up, there's a lot of narrative text and some starting code and places where you can enter your own code. Generally, top to bottom, top is like very beginner, bottom is getting really into the weeds with stuff. Some of them, so the callbacks, data sources, and inset figures, they start with figures, and the goal is to more or less try to reproduce those figures. And so I think I'll give you a quick overview of what each of these does, show you like some of the figures, and then we can all decide, do you want to walk through one or two of these together with me leading, or do you want to like have independent work time, try some plotting? So think about that as I give you the overview of each of these notebooks. Right. So plot adjustments is more or less just kind of some highlights from the YT docs page on how to modify plots. So if you're brand new to YT, this is maybe a useful one to walk through. If you have used YT a bit, you'd probably be a little bit bored by this notebook. They're more or less things that like I've noticed people ask questions about when they're new to YT. In terms of like, how do you make your plot look a certain way or do a certain thing? This second notebook on callbacks will reproduce this figure here, which is an off-axis slice with array on it, with in-plane annotated velocity vectors and a temperature field. So it's like a lot of callbacks layered on top of each other that we can work through. And described in detail below there, what it actually is. This data sources one is all about providing data sources to your plotting functions in order to subset the data that is being plotted. So this first example is just plotting for just a sub-selected sphere in a data set, and then layering on other data source objects as we go. This one is maybe fun, but what this one does is it walks you through creating projection plots with both grid-based and SVH data of density fields, and then estimating like how much mass that represents in your image. Because if you project density, you get mass per unit area. And so if you take the pixel area and multiply that, you can calculate the total mass in your image. And it does variably well depending on things like the size of your image buffer or the data set type. So this like walks through that in gory detail, which if everything else seems boring, I'd say maybe you should work on this one on your own. I don't think I want to walk through it with everybody live because I think it'll bore most people. And then this last one is all about wrangling axes. So it's creating inset figures where you have some zoomed in big figure and then a small little extra axes that gives you like an indication of the whole data set. Because one of the things about YT plotting is that all of it's built on Matplotlib under the hood, but it lets you access all of those underlying Matplotlib axes. So you can do some fun stuff by like going down to the Matplotlib level, extracting axes, adding axes, and monkey patching your way to create figures like this. This is one geo example using that same data set that was in the volume rendering of creating a zoomed in map in a little locator inset map. Yeah, so I'd say first, maybe show of hands, who would prefer doing a walkthrough one or two notebooks versus having some independent plotting time? Let's start with walkthrough. Raise your hand. One, two. And is everybody else independent plotting time? Just don't care.
Change my mind.
Okay, so probably leaning towards walkthrough. And then in terms of like what notebooks to walk through, I think like my inclination is to walk through either the, well, we probably could get through both the callbacks and the data sources in this amount of time. I'd probably go with those and then leave the others for you for independent study. Yeah.
I'm also, for various reasons, trying to download these rather than using the load sample functionality. But I managed to locate the isolated galaxy dump, but training cosmology, I don't know. It's a collection of files and YT.
It's multiple data sets.
But
Yeah,
load
so-
sample just gives you one of those types.
Load
of
sample was
the-
the last one.
Just the last one. I tried to supply like one of the DD00 blah whatever ones. It says it's an unsupported format. Potentially, it's the RD file. Or
So you can do either, and you need to, so the folder name is ED and a number. So it should be that / that again, which is the actual file name.
Oh, they're not the five, I see, right, so within that is this, yeah,
Like DD0046/DD0046.
and it works, I get you, yeah.
Yeah, if you just do a load sample tiny cosmology, I think it just gives you last, what was the time steps, right? Cool. Okay, well, I guess in absence of other votes, I think I'll do some walk through the let's start with the data sources one. I think it's a little bit simpler than the off axis fallback layering. And I think rather than like walking you through line by line, I'll pause now and then have you do some live coding to see if you can figure things out. Okay, so this plots 01, choose your own plotting adventure 03 data sources, the notebook that we're at. Yeah, so like I said earlier, I think all of the YT plotting functions either accept as an argument or a keyword argument a data source variable that lets you limit what data is actually plotted. So part one of this is to make a slice plot of a sphere region. That looks like this or something similar. Doesn't have to be this data set, not super important for this notebook. Some conditions to make it extra interesting. So if you, after we create our sphere object, it'll have some sphere center. So you probably want your slice plot to use that same center for the center of your plot. And then in order to actually just encapsulate the sphere region that's being plotted, you can set the width of the slice plot to twice the radius of the sphere that you use. So this first cell is using Enzo Tiny Cosmology. You can replace this with any of the data sets you have locally if you want. Yeah, so starting point is import, you load your data set, choose a field you want to work with, and write some code to find out where your maximum value is. Build the sphere object, and then use it to create a slice plot. Everyone feel good about trying to do that on your own for like 5-10 minutes?
Yeah. Oh, should we check in 5 minutes?
Yeah, check in 5 minutes.
Okay.
And if you get stuck, feel free to like raise your hand and I can come over and try to help. Although, does anyone want further explanation of what you're trying to do here?
Oh.
How is this compared with the convection?
It's not terrible. I think like as long as you use like a decent buffer size, it's like 21% relative error or so. For showing it on screen is probably fine. But there's like some interesting behavior as a function of buffer size where like that it's like the relative error does generally go down. But there are like weird jumps and stuff that like I don't understand at all, but like
Only one.
on axis and off axis. Well, I guess not. But based on axis is very good.
Even it should be.
It's like almost exactly precision. But everything else is off axis period more on for off axis. It's just
Even when I implemented the operative for operators. The method should be conserving. Yeah. But I guess I should
Yeah.
It's last word.
I didn't actually try it with Octree. It was one of at the end of that notebook I have things to try.
I'll
Try it with Octree. You started a timer.
Just about coming up on 5 minutes, so I'd say anytime now.
Okay, anyone successful? All failed. Okay, let's walk through this real quick. Okay, so at this point we have a data set and a field. So first thing we want is to find where this field is a maximum across the whole data set. So this gets into our data objects. So what I'll do is create, I will comment all of this, run this cell. Bunch of extra cells. So I'll create my data object here. And remember, there's lots of options for all of the quantities under here. And there are also multiple ways to do. I do this max location. So this one, if you look at the doc string for this, it accepts the field. It returns. Return is not actually super obvious, so let's just do it. So what you get out is the maximum value itself, and then the XYZ position of the maximum value. So let's put this into a variable, and then say location is actually, but so we'll say maximum law access ID for access ID in range 1 to 4. So this is just cleaning up that output so that we get a single array for the center value that we want, and making sure that it is just an array attached to our data set object. So next step is we want to create a sphere object centered there. So let's say SP equals ds dot sphere, location of that maximum, and then the radius looks like now our sphere. So now all we need to do is make a slice plot. Slice plot data set. This not super important. Remember which one it was. Through a field, and then we supply our data source argument here. That equals our sphere object. Also, let's put the center at the same location and fit width equal to our sphere radius. That works. No, wow, they do. So. It's probably however it's output. Here. Let's look at it.
I always figured it's in the range.
Yeah, width has to be in the array.
Yeah, it's really not mid range.
Oh, it has to not be in the array? Okay.
Okay, and why is it not using our data source? That problem. Well, maybe the width is not quite right.
Yeah, because if the width of the radius, it should be fully contained.
There's the radius. Cool. Okay, so that's how you do that plot. Any questions on that?
I like this because this sort of thing is a nice illustration when you start to make complex shapes that you're actually selecting the data that you think you are. So when you start, poking holes in spheres or disks or adding things together, you can do this sort of thing and you will see exactly the shape, or you should.
I will actually, I will show that tomorrow, actually.
All right,
Yeah.
that's gonna be fun. Okay, cool. I love that.
All right, on to figure 2. Pretty much the same thing, except instead of a sphere, we're going to use a cut region. So, which I don't think we talked about today, and I don't know that many people use it, but I occasionally have fun with it. So this is a way of masking data in order to just select certain data ranges. So, this plot, you probably can make this plot just by adjusting color limits, but we're going to do it with conditionals instead. And since we didn't go through this today, I think I will first just walk through how to make a cut region.
I'll also talk about it tomorrow.
You will?
Yes.
Should I skip this then?
It's up to you, but
You probably can speed through it.
Yeah, okay. Okay, so I always have to look at the example here. So you give it a data source to apply a cut region to, and then you give it a list of strings that are the conditionals that you want to apply. So for example, this object here looks like any of our data objects, gas temperature field less than n to the 3, except you'll notice the quotes. So it is a string. It's not an actual evaluation of that. It happens inside the cut region object. So if we want to say our cut region is equal to everywhere the temperature is above a number, I think I did. Yeah, we would do object gas temperature greater than 185. That should create our cut region. And then I'll leave this to you, make a slice plot again, just over the whole domain of the temperature field, using that data source to limit your plot. it'll be all the same arguments as before, just set your data source equal to the cut region that we just made.
Can I make a comment with the data source?
Mhm.
I mean, one advantage of using the data sources is that if you want to, as you just did, like if you just want to plot gas that's above some temperature, that's useful. But also again, like if you have a big data set, it makes a difference between everything is going to be red and only a subset is going to be plots. Whereas if you pass in the data source, then only things within the data source is actually going to get reds and plots. Which means that if you want to plot a tiny corner of your simulation, then you should use data source. Otherwise, you're going to read absolutely the entirety of the simulation and then just plot everything and then just zoom on the corner. It's going to be much smaller.
Start filling this in. So slice plot, data source, axis. And so first we're gonna plot this temperature field and provide our cut region for that data source. What we should see is all the places where the temperature is above some value. But what's cool about using this sort of cut region is when you, oops. Is that you can instead plot a different field that meets that condition. So this plot would be the density values everywhere that temperature is above that value. So you can start layering all of these conditionals on top of the fields you're plotting and come up with a lot of ways. So like this plot would be harder to do just by adjusting color mass, whereas the temperature one you could just change the Z limit so we get this plot. Okay. And then lastly, we're going to combine these two plots. So we're going to use this ds.bool data object to combine our two data objects that we already have. And check out the doc string. First thing you've provided is a string. That can be any one of these things, and or XOR not or and then a list of all the data objects that you want to combine. So I'll give you a minute to figure out how to combine our data source. Oh, sorry, I misread that. So instead of a list, these are individual objects. I have 3 arguments here. Give you a minute to fill that out. Okay, so a Boolean combined object where both the conditions are met. We want an and here, and then we just give it our sphere and our cut region, which I called underscore R. Out our combined object, and then let's make another slice plot that uses this combined data object and see if we get something close. Don't think we will. I think I probably used axes or something. But I'm going to go back up to our initial sphere plot, just copy paste that. Actually, down here. And then instead of the sphere data source, we're going to use this combined data source and change the axis. And so you see, you still get the spherical selection, but now we're only seeing the density values where you're within the sphere and above that temperature cutoff. And then also, just as a note, like I said, all of the plotting methods except a data source argument. The phase plot, it's just that first argument. So let's say you make this figure and you want an actual distribution of values from within this combined data source. You can use phase plot to do that and just give it that same data source. So to do that, you would just do dot phase plot find, and let's see, we're doing density, temperature, mass. Yeah. Your distribution just wrote that subset of values. So cool. So that's what I had for that notebook. About 10 minutes before the start of the lightning talk. So I think what I'll do is walk you through a little bit of the layered callbacks one, which was this one. Oh, I will say, if you all look through these later on your own, there is this solutions folder where it has everything filled out for how to actually do it. If you get stuck, let's see how these plots are made. Go to that folder. Right. Okay. So this is a off-axis slice plot with a lot of things on top of it. Here's a list of all the things on top of it. So there's an array that passes through the maximum density value of the data set. Has some conditions on the start point and end point of the array, which are mostly important just if you wanted to exactly recreate this image. And then the off-axis slice is oriented so that this array lies entirely within the plane of the image. So to do that, you got to start thinking about like normal vectors of the plane relative to the direction your array is traveling. And then it uses a couple of callbacks to add annotations on. So there's annotate marker for the start and the endpoint of the array. And then there's an annotate velocity and an annotate contour for the velocity and the contour temperature. The black lines are contoured temperature values. So yeah, so I think we can do a little bit of this. So this is again using isolated galaxy. So first step in this, if we wanted to recreate this exactly, is to find the location of that maximum value again, which we've already done before. So I'll do this real quick. Probably we'll go back to the other one, paste it. Not define that yet, so I will just take that easily with that. That's the value. Now we have the location of the maximum, which is pretty much in the center. Not surprising when you look at the plot, the slice plot. So what we're going to do here is create an array that passes through that max value, but because I like the look, I want the array to pass through and have the maximum value located at the center, which is math to do. But since our maximum value is in the center, I'll cut this a little short and just have the array start and end point. The domain left edge, main right edge. And our array is a s.array start and end point. And skip for now. we have left. Yeah, we'll see what happens. Okay, so. Yeah. So the goal now is let's just, I think in the time left, let's just get a slice on screen with our array on it. And so what we can do. So this slightly more complicated bit is just, so if we're doing an off-axis slice plot and you want the array entirely within the image that you have, you have to pick a normal vector for the slice plot that is perpendicular to your array. So this code here leads you through how to do that. But we're going to save it for now. And let's just plot our off-axis plot. And then array annotation. So there's an annotate array. Just look at array. I'll draw a that on screen for you. But we cannot actually see. I'm not. So depending on the normal vector you choose, you may or may not see this, right? That's why I have you go through and actually calculate what normal vector you get at that. And then, so to add on the other fields, they're just more annotations. So the annotate marker is pretty easy. Annotate marker, give it just a point in space. And a lot of the annotations you can give it in either 3D spatial coordinates of your data set or on-screen coordinates. The default though is just your 3D spatial coordinates, but there is this coord system argument that you can change if you want to supply it in the other coordinate systems. But we wanted to annotate the start of the array. A start point. Put it up on there. And you kind of see it over at the edge there. And if we also wanted to annotate the endpoint. So see a little X there. They're marked X. And then the other annotations. So for off axis, so annotate contour is pretty self-explanatory. We'll just put a contour on. Yeah.
Did you, maybe I missed this, did you talk about how because these are in data space, if you zoom and pan, still look correct?
Will not.
Zoom out by a factor of 0.1 or something.
Well, I understand. Yeah, so because we define those in terms of the data space, when you zoom out, your lines here will be adjusted correctly, whereas if you define them in figure space, they would still end up in the same place relative in your figure. Right, so annotate contour is pretty self-explanatory. You can check out the docs for that. Just contour is a field on your plot. For off-axis plots, this annotate C quiver is very useful, and I'm just going to pull up docs for this. So what this will do is once you create an off-axis slice plot or projection plot, you can access additional fields that will plot the component of that field in your slice. So if you're going to plot the velocities, this would be cutting plane velocity X and cutting plane velocity Y. And so these are the components of these 3D vectors that lie in the plane that you are plotting. Which is very useful because you can imagine a lot of annoying trigonometry to figure that out yourself. And this lets you do it in a single line. Pretty cool. Yeah, so that's all the elements of how to make that plot. And I think I'll leave it at that. 5 minutes before lightning.
Right. Thank you, Chris. Fantastic.